Hello everyone. In this video we are going to solve some problems on the Rolle's mean value theorem. So let's begin with a very basic example. It says that verify Rolle's theorem for y is equals to sin x by e power x in close 0 to pi. So let's solve this problem. So first thing first, I have a function f of x is sin x by e power x. So first I would check its continuity. Next, I would check its differentiability. So, sin x and e power x are both continuous in 0 to pi, and e power x is anyways positive number. So, fx is always continuous, and similarly sin x and e power x are differentiable and e power x is always a positive number. So, sin x by e power x is always differentiable. Now, let me check the third condition. Let me check the value of the function at 0. It is 0. And the value of the function at pi. It is also 0. Now, so the three conditions of the Rolle's mean value theorem are satisfied. Now, let's verify whether the claim is true or not. So, I am computing f dash x. So, it is e power x into cos x minus sin x into e power x by e power x whole square. So, I have used the quotient rule to compute the derivative of the function. Now I am equating it to 0, so I would get e power x into cos x minus sin x is 0. So basically this would lead me to cos x minus sin x is equals to 0 or tan x is equals to 1. So I can see that x is equals to pi by 4 is a solution in the open interval 0 comma pi to this equation tan x is equals to 1. This means that x is equals to pi by 4, the derivative of the function is 0, and this verifies my Rolle's theorem. Now let's proceed to second question. It says that verify Rolle's theorem for y is equals to mod x in close minus 1 to 1. So first things first, let us check the condition for continuity of the function. Of course, we know that mod x is continuous over the entire real number. Next, let us check the differentiability. We know that mod x is not differentiable at x is equals to 0, and the 0 lies between minus 1 to 1. So basically my function y is equals to mod x, or f of x is y is equals to mod x, is not differentiable in the given interval minus 1 to 1 open. Hence, I can say that the Rolle's theorem is not applicable for this function. The Rolle's theorem is not applicable. So, the Rolle's theorem is applicable if and only if the premises are satisfied. That is, the first three conditions are satisfied. Then only the Rolle's theorem is applicable. So, here I can say that the Rolle's theorem is not applicable. Now, let's proceed to the third question. Okay, this is a very interesting and very nice question. You will learn a lot in this example. So it says that between any two roots of the equation e power x cos x is equals to 1, we need to prove these things, that there exists at least one root of tan x is equals to 1 and there exists at least one root of e power x sin x is equals to 1. So now the basic idea here in this problem is I would use the corollary which we have learned in the previous video, that between any two roots of f of x is equals to 0, I have at least one root of f dash x is equals to 0. So I would use this key idea in this problem. So I would assume a function first, f of x is e power x cos x minus 1. So since this is the given function to me, now I would differentiate this. I would get e power x into cos x derivative is minus sin x plus cos x into derivative of e power x is e power x, and minus derivative of 1 is 0. So this is nothing but e power x into cos x minus sin x. So I know that between any two roots of this function, I will always have at least one root of this function, and the root of this function is nothing but the root of tan x is equals to 1. So I have proved my first question. Now how do we prove this second point, that there is a root of e power x sin x is equals to 1? See, the key idea is same, that we need to use this fact that between any two roots of f of x is equals to 0, there is at least one root of f dash x is equals to 0. But how do we use it here? So what I am trying to do is, I am manipulating this given equation in this way. So I am taking e power x to the other side of the equation, and I have got cos x is e power minus x. And now I am bringing all the terms to one side of the equality, and I am assuming a new function fx, which is e power minus x minus cos x. Now I will try to differentiate this function. So let us do it. F dash x is equals to, the derivative of e power minus x is e power minus x into minus 1, minus derivative of cos x is negative sin x, so this becomes plus sin x. So I know that between two roots of f of x is e power minus x minus cos x, I would have at least one root of this function, that is its derivative. So it means I would have at least one root of minus e power minus x is equals to minus sin x. It means that e power minus x is equals to sin x, and it simply means that e power x into sin x is equals to 1. So let me write it again for you. If this is messy, sorry for this. So this nothing but sin x is equals to e power minus x, and this implies e power x into sin x is equals to 1. So what we have done is, we have manipulated the given equation in this way, that is, we have taken the e power x to the other side, and now we have assumed a new function f of x, which is e power x minus cos x, e power minus x minus cos x. And now we have used the Rolle's theorem on this function, and we have differentiated this and equated it to 0, and we have got the desired result. So we have also proved problem number 2. Now you can try another manipulation here. What you can do is, it might be interesting, I have not tried, but you can see that you can manipulate this function in this way also, and now you can assume a new function which is e power x minus secant x, and you can apply the Rolle's theorem on this function as well. So the key idea in this problem was this, the first one, and then we are manipulating the given function and differentiating it. So I hope you like this problem. Now let's move on to the next one. This is also a very interesting problem. Let a, b, c, d be non-zero real such that 6a plus 4b plus 3c plus 3d is 0, and then the equation ax cube plus bx square plus cx plus d is equals to 0 has at least one root in 0 comma 2 closed interval. We need to prove this question actually. So how do we proceed? Okay, I need to prove that this equation ax cube plus bx square plus cx plus d is equals to 0 has at least one root in 0 to closed. Okay, I will use the same idea once again which we have used in the previous problem, that between any two roots of f of x is equals to 0, I have at least one root of f dash x is equals to 0. So this function is my f dash of x here. I need to prove the roots for this. So what will be my f of x? Upon integrating this, I would get integration of x cube is x power 4 by 4 plus bx cube by 3 plus cx square by 2 plus dx. This is my new function f of x, which I have obtained upon integrating this function. Now let us try to apply the Rolle's theorem on this. Okay, so this function is anyways continuous and it is differentiable. Now let us check the value of this function at 0. It is 0. Let us check the value of this function at 2. It is a into 2 power 4 16 by 4 plus b into this is 8 by 3 plus c into this is 4 by 2 plus this is d into 2. So f of 2 is nothing but 4a plus it is 8b by 3 plus it is 2c plus 2d. Now let me multiply this by 3. So this is like 1/3 into this is 12a plus 8b plus 6c plus 6d. So I can see that f of 2 is 2/3 of 6a plus 4b plus 3c plus 3d. So this is given as 0 in the question. 6a plus 4b plus 3c plus 3d is given as 0. So I can see that this function f of x is continuous, it is differentiable since it's a polynomial function, and f of 0 is 0, f of 2 is 0, hence Rolle's theorem is applicable, and by Rolle's theorem we can say that there is at least one root of f dash x is equals to 0. And what do you mean by f dash x? This is nothing but f dash x of this function, which is ax cube plus bx square plus cx plus d. So we have proved that there is at least one root of this equation, ax cube plus bx square plus cx plus d is equals to 0. I hope this is clear and you like this problem. So the key idea again is we are using the fact that between two roots of f of x is equals to 0, there is at least one root of f dash x is equals to 0. This is the key idea in the previous two problems. So let's move on. Okay, there is another question which says that f of 1 is g of 1, f of 2 is 4, g of 2 is 1 by 2, f and g are differentiable. Now I need to prove that f dash x is 3x square gx plus x cube into g dash x for some x belongs to 1, 2 open. So let us see how do we proceed about this problem. I have given that f dash x is 3x square times gx plus x cube times g dash x. Now again I would try to integrate this function and apply the Rolle's theorem on that integrated function like I did in the previous question. So let us see what is the integral of f dash x. It is fx. So and this entire thing, this is nothing but the differential of x cube times gx. So you can apply the product rule here, x cube into g dash x plus g of x into 3x square. This is the derivative of x cube times gx. So now I will assume a new function h of x, which is nothing but f of x minus x cube times gx. So what I have done is I have integrated this function and then I have brought all the terms to one side of the equation. So this is my new function hx. So now I will try to apply the Rolle's theorem on hx. So let us check h of 1. h of 1 is f of 1 minus g of 1, which is 0, since it is given to me that f of 1 is g of 1. And let us check h of 2. h of 2 is f of 2 minus 8 times g of 2, which is again 0. If I plug in the values given to me, I would get this as 0. And since f and g are differentiable, I can say that h is also differentiable. So h is differentiable, h of 1, h of 2 are 0. Then I can claim by Rolle's theorem that there exists at least one c belongs to 1, 2 such that h dash of c is 0. It means there exists at least one root of h dash x is equals to 0, which essentially is a root of this equation, since h dash x is f dash x minus the derivative of x cube times gx. So you would get the root of this equation. So I hope this is clear to you. In the previous three problems, we have applying the same key idea again and again, that between any two roots of f of x is equals to 0, there always exists at least one root of f dash x is equals to 0. We have been using this idea repeatedly. So let's move on to the next question. Okay, we have extended this problem to double derivative here. So suppose that f double dash x exists everywhere and f of x1 is equals to f of x2 is equals to f of x3, where x1 less than x2 less than x3, then I need to prove that there exists at least one c in x1 x3 open interval where the double derivative of this c is 0. So till now in the Rolle's theorem we have claimed that the single derivative of function is 0 between two roots of f of x. So now we have extended this to double derivative. So let's see how would we solve this problem. So since f of x1 is equals to f of x2, I can say that there exists some, let us say a belongs to x1 comma x2 such that f dash of a is 0 by Rolle's theorem, and since f of x2 is f of x3, I can claim there exists some b belongs to x2 comma x3 such that f dash of b is 0. Of course the premises are satisfied since f is double differentiable everywhere, f is definitely continuous and differentiable, so we can write these 2 points by Rolle's theorem. And now what would I do is I would apply Rolle's theorem again on f dash x. First I have applied the Rolle's theorem on fx, now I would apply Rolle's theorem on f dash x. How would I do it? See, f dash a is 0 and this is equal to f dash b. So f dash has two roots, namely a and b, and by Rolle's theorem I can say that the derivative of f dash, which is nothing but f double dash x, has a root in open interval a comma b. That is, there exists a c in open interval a comma b such that f double dash c is 0, and since c is in open interval a comma b, I can write that c is also in open interval x1 x3. So I hope this problem is clear to you. What we have essentially done is we have applied the Rolle's theorem twice, once on f of x, second time on f dash x. So similarly we can apply it n number of times and we can go till nth derivative. So I hope the problems, the examples which you have solved in this video are pretty much clear, and if you have any queries then let me know in the comment section. I hope you enjoyed watching this video, and there is one more question which you can try yourself, and maybe if you get the answer you can put it in the comment section. And the key idea is the same. We need to integrate and obtain a function, and we need to apply the Rolle's theorem on that function. So I hope you try this question, and if you want hints then let me know. I would give you the hints in the comment section. And I hope you enjoyed watching this video, and if you did, like, share and subscribe. And in the next video we would be learning Lagrange's mean value theorem. So until then, keep enjoying mathematics, keep learning. Thanks for watching.